In a three-phase delta Y transformer, the X0 terminal represents the neutral point of the Y-configured secondary winding. It is typically grounded to achieve several important objectives. Firstly, grounding the X0 terminal provides a stable reference point for voltage measurements. This ensures that the voltages measured across the secondary windings are accurate and consistent. Secondly, grounding the X0 terminal helps to ensure that the secondary voltages remain balanced. In a balanced system, each phase voltage should be equal in magnitude and 120 electrical degrees apart. Grounding the neutral point helps to maintain this balance, preventing voltage imbalances that can lead to equipment damage or malfunction. Thirdly, grounding the X0 terminal provides protection against voltage surges and transient currents. These surges can occur due to lightning strikes, switching operations, or other electrical disturbances. By providing a low impedance path to ground, the grounding system helps to divert these surges away from sensitive equipment, protecting it from damage. The transformer case should also be grounded for safety reasons. Grounding the case provides a path for fault currents, preventing them from flowing through personnel or equipment. In the event of a fault, such as a short circuit, the fault current will flow through the grounding system back to the source. This will cause the circuit breaker or fuse to trip, interrupting the flow of current and preventing electrical shock or fire. Additionally, grounding the case helps to dissipate heat and reduce electromagnetic interference, also known as EMI. Heat is generated within the transformer due to core losses and winding resistance. Grounding the case helps to conduct this heat away from the transformer, preventing overheating and extending its lifespan. Electromagnetic interference can be generated by the transformer's magnetic field. Grounding the case helps to shield the surrounding environment from this interference, preventing it from disrupting sensitive electronic equipment. It is crucial to ensure that the transformer is properly grounded to avoid electrical hazards and ensure safe operation. Improper grounding can lead to electric shock, equipment damage, and even fire. The grounding system should be designed and installed by a qualified electrician in accordance with applicable electrical codes and standards. The grounding system should comply with the National Electrical Code, specifically Article 250, which covers grounding and bonding requirements. The size of the grounding conductor should be determined based on the size of the transformer and the available fault current. The grounding electrode should be a rod, pipe, or plate that is buried in the earth and provides a low impedance path to ground. The grounding electrode should be located as close as possible to the transformer. All grounding connections should be made using approved connectors and should be properly tightened to ensure good electrical connection. The grounding system should be inspected and tested regularly to ensure that it is functioning properly. Grounding is a critical aspect of electrical safety. Grounding the transformer case is essential to protect personnel from electrical shock hazards. If a live conductor inside the transformer comes into contact with the metal case, the case will become energized. If a person touches the energized case, they could receive a severe electric shock. However, if the case is properly grounded, the fault current will flow through the grounding system, causing the circuit breaker to trip and to energize the circuit. This will prevent the person from receiving an electric shock. Grounding the X0 terminal is crucial for maintaining a stable and balanced voltage supply. In a Y-connected system, the neutral point, or X0 terminal, is the common point of the three-phase windings. If the neutral point is not grounded, the voltage on each phase can fluctuate, leading to voltage imbalances. These voltage imbalances can cause equipment damage, reduced efficiency, and increased energy consumption. Grounding the neutral point provides a reference point for the voltage, ensuring that the voltage on each phase remains stable and balanced. Grounding also helps to protect against voltage surges and transient currents. These surges can be caused by lightning strikes, switching operations, or other electrical disturbances. If these surges are not properly grounded, they can damage sensitive electronic equipment. Grounding provides a low impedance path to ground, diverting these surges away from the equipment and protecting it from damage. The specific requirements for grounding a transformer will vary depending on the size and type of transformer, as well as the applicable electrical codes and standards. It is essential to consult with a qualified electrician to ensure that the transformer is properly grounded. Improper grounding can lead to serious electrical hazards, equipment damage, and even fire. A proper grounding system consists of several components, including the grounding electrode conductor, equipment grounding conductor, and the bonding jumpers. The grounding electrode is a conductor that is buried in the earth and provides a low impedance path to ground. The grounding electrode can be a rod, pipe, plate, or other approved conductor. The grounding electrode conductor connects the grounding electrode to the grounding bus in the electrical panel. The equipment grounding conductor connects the non-current carrying metal parts of electrical equipment to the grounding bus. Bonding jumpers are used to connect different metal parts of the electrical system together, ensuring that they are all at the same electrical potential. The size of the grounding conductor should be determined based on the size of the transformer and the available fault current. The grounding conductor should be installed in accordance with the National Electrical Code. The grounding system should be inspected and tested regularly to ensure that it is functioning properly. The National Electrical Code, or NEC, provides detailed requirements for grounding electrical systems. Article 250 of the NEC covers grounding and bonding requirements. This article specifies the types of grounding electrodes that are permitted, the size of the grounding conductors that are required, and the methods for installing the grounding system. It is essential to comply with the NEC requirements to ensure that the electrical system is properly grounded and safe. When grounding a 480 volts 3-phase delta/208 volts 120 volts Y transformer, special attention should be paid to the following. Firstly, the size of the grounding electrode conductor must be sufficient to handle the available fault current. NEC Table 250.66 provides guidance on selecting the appropriate size of grounding electrode conductor. Secondly, the grounding electrode must be properly installed and connected to the earth. The grounding electrode should be located as close as possible to the transformer. Thirdly, the equipment grounding conductor must be properly connected to the transformer case and to all other non-current carrying metal parts of the electrical system. Finally, the grounding system must be inspected and tested regularly to ensure that it is functioning properly. When selecting a grounding electrode, several factors should be considered. Firstly, the soil conditions at the site should be taken into account. The soil resistivity will affect the effectiveness of the grounding electrode. Secondly, the size and type of transformer should be considered. The grounding electrode should be sized to handle the available fault current. Thirdly, the applicable electrical codes and standards should be followed. The NEC provides specific requirements for grounding electrodes. There are several different types of grounding electrodes available. Rod electrodes are commonly used and are driven into the earth. Pipe electrodes are similar to rod electrodes but are made of pipe. Plate electrodes are buried in the earth horizontally. Concrete encased electrodes are encased in concrete and buried in the earth. The choice of grounding electrode will depend on the specific site conditions and the applicable electrical codes and standards. When installing a grounding electrode, several precautions should be taken. Firstly, the grounding electrode should be located as far away as possible from any underground utilities. Secondly, the grounding electrode should be driven or buried deep enough to reach permanent moisture. Thirdly, the grounding electrode should be protected from physical damage. Fourthly, the grounding electrode should be properly connected to the grounding electrode conductor. The grounding electrode conductor should be connected to the grounding electrode using an approved connector. The connector should be properly tightened to ensure a good electrical connection. The grounding electrode conductor should be protected from physical damage. The grounding electrode conductor should be run in a conduit or other protective raceway. The grounding electrode conductor should be continuous and unbroken. The grounding electrode conductor should not be spliced or jointed. The equipment grounding conductor connects the non-current carrying metal parts of electrical equipment to the grounding bus. The equipment grounding conductor should be sized in accordance with NEC Table 250.122. The equipment grounding conductor should be run with the circuit conductors. The equipment grounding conductor should be connected to the equipment using an approved connector. The connector should be properly tightened to ensure a good electrical connection. Bonding jumpers are used to connect different metal parts of the electrical system together, ensuring that they are all at the same electrical potential. Bonding jumpers should be used to bond together metal conduits, metal enclosures, and other metal parts of the electrical system. Bonding jumpers should be sized in accordance with NEC Table 250.102. Bonding jumpers should be connected to the metal parts using approved connectors. The connectors should be properly tightened to ensure a good electrical connection. The grounding system should be inspected and tested regularly to ensure that it is functioning properly. The grounding system should be inspected visually for any signs of damage or deterioration. The grounding system should be tested using a ground resistance meter to verify that the grounding resistance is within acceptable limits. The grounding resistance should be measured between the grounding electrode and a remote point in the earth. The grounding resistance should be less than 25 ohms. If the grounding resistance is greater than 25 ohms, the grounding system should be improved. The grounding system can be improved by adding additional grounding electrodes, by improving the soil conductivity, or by replacing the existing grounding electrode with a larger one. Grounding is a critical aspect of electrical safety. Proper grounding can prevent electric shock, equipment damage, and fire. It is essential to consult with a qualified electrician to ensure that the electrical system is properly grounded. Remember, safety comes first.